Hi everybody, today we are going to talk about lines and planes in space. So the first thing we're going to talk about is how to make an equation of a three-dimensional line in space. So for these, there are formulas to do this, but I want you to understand where the formula comes from. But I do want to point out that we are going to be using vectors to make these equations, and we're actually going to have a parametric set of equations. So to make an equation of a line in space, you need two things. You need to know one of the points on the line, and you need to know a vector that is parallel to your line. So here we are given a point, x1, y1, z1, and we're given vector v, which is ABC, which is parallel to our line. So first of all, there's something really important we need to remember about parallel vectors. If two vectors are parallel, we know that they are scalar multiples. So we can make the statement that vector PQ is equal to t times vector v, where t is just some scalar multiple. So we know that we can create a vector for PQ. We can use the point that we're given and then any other point x, y, z, and we can turn that into component form. So this will be our terminal, this will be our initial, so we can do x minus x1, y minus y1, and z minus z1. That is vector PQ. Well, vector v, or t times vector v, we know that when we multiply a vector by a scalar, we essentially just multiply each component of your vector by that scalar. So it's just going to be a t, b t, and c t. I essentially just went in and multiplied a, b, and c by our scalar. So this is what we get. Well, we have already made the mathematical statement that vector PQ is equal to a scalar multiple of vector V. So we know that these two vectors should be equal. Therefore, we can go through and we can set the corresponding parts equal to each other. We can set these equal to each other, these, and these. So I'm going to go ahead and do that really quick. We know that x minus x1 should equal a times t, some scalar. Y minus y1 should equal b times t, and z minus z1 should equal c times t. Now, of course, we are making an equation, and we want to know what x, y, and z are equal to because it is an equation. So we're going to go through and solve for each of those variables. So x is just x1 plus a times t. Y is just y1 plus b times t. And z is just z1 plus c times t. So you can see here that we actually have a set of parametric equations for this line. And the parameter in this case is going to be t, which is our scalar multiple. But you'll see that that parameter shows up in all three of our parametric equations. So here's the formula that we just showed how to find. So x is going to equal x1 plus a times t, y equals y1 plus b times t, and z equals z1 plus c times t. And of course, that's given one point on your line and a vector that is parallel to your line. Those are the two things we need to make an equation for a line in space. Now from there, we can rewrite our set of parametric equations as what's called a set of symmetric equations. So imagine you went through and you solved for t for each of these. If I was solving for t here, I would subtract x1 and then divide by a, and here's what I get. If I solve for t here, same process, and same for my z values as well. So since they would all be equal to t, they are equal to each other. So this is what's called a set of symmetric equations. And essentially what we're doing is eliminating the parameter. So you will be asked to write your equations both as parametric and symmetric. Okay, let's give this one a try. Here we want the parametric and symmetric equations of the line that passes through the point 1, negative 2, 4. So this is just going to be x1, y1, and z1, and is parallel to this vector v. Well, that is going to be our a, b, and c values. Oh, and by the way, just a little bit of terminology. We call that our direction vector. because if it's parallel to this vector, it is going to essentially determine the direction of your line. Okay, so now we have everything we need, and we're just going to use the formulas we just found. So we'll say x equals x1 plus a times t, y equals y1 plus b times t, and z equals z1 plus, which will become a negative, 4 times t. So this is our set of parametric equations. These are parametric. But now they would also like us to find the symmetric equations. So I'm going to go through and solve each one for t. So here t is going to be x minus 1 over 2. For our second one, t is going to be y plus 2 over 4. And here t is going to be z minus 4 over negative 4. And since they are all equal to t, they are all equal to each other. So we can write it as our set of symmetric equations. There you go. And that's all we have to do for these types of problems. All right, go ahead and pause the video and give this one a try. All right, so go ahead and check your parametric equations and then your symmetric equations below. Okay, so now let's try, it's the same general theory on how to create the equation. However, we're given different information here. So here, we want to find the equation of the line that passes through these 2 points. So here we're actually given 2 points. So we are going to use this as x1, y1, z1. That's great. We have a point, but we need to find a direction vector. We need a vector that is parallel to this line. Well, luckily for our direction vector, we can just create the component form. We can create the component form of this vector because the component form of any vector is always going to be parallel to the original vector. So essentially, we just have to create our own parallel vector. It's easy enough to do. Let's use this as the terminal and this is the initial. So 1 minus negative 2 is 3. 3 minus 1 is 2, and then 5 minus 0. So these are going to be our A, B, and C values. Now from here, it's exactly the same as what we just did. We're just going to use our little formula. So x equals negative 2 plus 3t, y equals 1 plus 2t, and z equals 0 plus 5t. So those are our parametric equations. And now for our symmetric ones, we essentially solve for t and set them all equal. So we have x plus 2 over 3 is going to equal y minus 1 over 2, which is going to equal z over 5. So here we have the parametric equations, and here we have the symmetric equations. All right, go ahead and pause the video and give this one a try. Okay, so remember for this one, you do have to create your own parallel vector, which will essentially just be the component form of this vector. So this is going to be our direction vector, which tells us our A, B, and C values, and we're going to use this as x1, y1, z1. Plug them into your formulas, and you should be good to go. All right, so now we're going to talk about how to write an equation of a plane in space. So for this one, you actually need different sets of information. You still need to use or to know one point on the plane, but now you have to know a vector that is normal or perpendicular to the plane. So for lines, we wanted a vector that was parallel. For planes, we want a vector that is perpendicular. And the word normal, it just means perpendicular. So let's look at this figure below. We have a plane that has point P. So we're given one of the points. We are also told that vector n is the normal vector, meaning it is perpendicular to the plane that you see in blue. So just a side note, the reason why they're not using the word orthogonal, even though it essentially means the same thing, is orthogonal is directly related to two vectors, not a vector and a plane. So for that, we use the word normal. So here's our normal vector, and here's the point, and then we can create any other vector using Q, which is just any other point on the plane, x, y, z. So there's one really important thing that we need to know about normal or perpendicular vectors. So I'm going to highlight this part. Orthogonal to n. Hopefully you remember that orthogonal vectors have a dot product that is 0. So since these two vectors are orthogonal, we can say that the dot product of vector n and vector pq should equal 0. That is, by definition, how we tested whether two vectors are orthogonal. Okay, so let's see what vector n is. Vector n is defined as ABC. And we're going to need to make the component form of PQ, but that's no big deal. We'll just use this as our initial point, and we'll use this as our terminal point. So x minus x1, y minus y1, and z minus z1. And we know that the dot product should be 0 because, once again, the two vectors are orthogonal. So now we just have to actually take the dot product. So remember, we just multiply the corresponding parts of your vectors, and then we take the sum of those products. So we have a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. And this right here is actually the standard equation for a plane in space. So here it is repeated again on this slide. So when we are given a point on the plane and a normal vector, so a vector that is perpendicular to the plane, all we have to do is substitute our values for a, b, and c, which is from the normal vector, and x1, y1, z1, which is any point on your plane. So here's the standard equation, and they'll probably ask you to write your equation in general form. So essentially, they're just asking you to distribute this out and combine like terms. And they want x, then y, then z, and then your constant equals 0. So that's what general form is. All right, so let's see if we can give this one a try. Here, let's find the general form of the equation of the plane passing through this point. So this is going to be x1, y1, z1, and perpendicular to vector n. So this is going to be our a, b, and c values. So it's as easy as that. Now we just have to plug it into our formula. So we'll do a times x minus x1 plus b times y minus y1 plus c, which is 1 times z minus z1 equals 0. So this is the standard equation. Now we just need to put it into general form. So I'm just going to pretty much distribute everything out and combine like terms. So we're left with negative 3x plus 2y plus z minus 9 equals 0. And there you have it. So I do just want to point out this is slightly different than making an equation of a line, because instead of having a vector that is parallel, we need a vector that is perpendicular to the line. All right, go ahead and pause the video and give this last problem a try. Okay, so here, once again, these are going to be our x1, y1, z1 values, and this is going to be a, b, and c. So we just plug it into our formula, distribute, and combine like terms to place it into general form. Okay, that is all for today's lesson. Thank you so much for watching.